it. The first thing that we need to understand is why normal distribution. What is important about normal distribution? Why we care so much about normal distribution? And what is the difference of this distribution with the other discrete distributions that we learned last week, that we talked about last week? Okay, the first thing that it's important to talk about is that the normal distribution is over a continuous variable. Continuous variable meaning the variable that you have, your x, can take values over an interval of the real numbers. While previously we looked at distributions that they were discrete, so the values that they could take were always specific whole numbers, integers. This is the main difference that they have. Because of this difference, instead of using histograms in order to actually present the distributions, we are using curves. The normal distribution, you all of you have seen the bell curve before, and this is what represents basically the normal distribution. Now, why the normal distribution is important? There are many reasons why the normal distribution is important. The first one, the most important one, is that almost everything, almost all natural things follow the normal distribution. Almost everything that has to do with nature follows the normal distribution. Artificial situations follow other distributions. By saying that, I don't mean that there are no situations and variables in nature that they don't follow different type of distributions. Of course there are. But mostly when you are working with anything that has to do with nature, the biggest percentage of the situations of the variables follow the normal distribution. As a result, it is extremely important. The second important reason that the normal distribution takes our attention so much is that it can approximate when the number of trials, the experiments that we run, the data points that we have in the data set, when there are many, when we have many up above a specific number of data points in a distribution that is a discrete distribution, then that distribution, like the binomial, tends to approximate the normal distribution. So instead of using information from the binomial distribution, we can actually approximate it by using the tools that we have for normal distribution. Now, why is this important? Well, for us right now, in our era, this is not that important. For example, if I have 1,000 different trials for a specific experiment that has a probability of 0.32, and I want to find specifically what is the probability distribution for each one of the possible variables, this is something that I can easily put in Excel. It will give me the answers in a split second. In the past, though, when they didn't have this luxury of the different softwares, they had to calculate all this by hand. So instead of doing that by hand, especially when they had a big data set, they preferred to use the normal distribution in order to calculate the probabilities, because in the normal distribution, because of the continuity, because of the fact that the variable is continuous, they were able to calculate this using calculus with actually calculating just one integral in order to find the area that corresponds to the probabilities. That was the second reason why it was extremely important. Now, the third reason that this is important is that any distribution, no matter what the distribution is, if we take the sampling distribution and we focus on different samples of the entire population, then the sampling distribution of the sample means follows the normal distribution, independently of what distribution we have at the beginning. This is basically the central limit theorem that we will be discussing today. But this, by itself, it gives us so much information and gives to the normal distribution so much power that basically makes it the most important distribution of all. These are the main reasons why the normal distribution is important. Well, first of all, just to make sure that we understand, there is not only one normal distribution. There are infinite normal distributions. A distribution depends on its variable. The variable can be, for example, the height of the girls, 14-year-old girls in the United States. If I'm talking about this population, the population of the height of the girls, 14-year-old girls in the United States in 2017, then I'm talking about a population that follows, actually, the normal distribution. So it is a normal distribution. It's going to have its own mean and it's going to have its own standard deviation. The variable will be the height. In the same way, I can have a distribution that refers to the number of hours that any professor spends grading. Again, this may follow the normal distribution. It's going to have a mean and it's going to have a standard deviation. Each one of all these different normal distributions that they express basically variables that they can be anything that follows this. There are infinite. There are infinite number of them with different means and different variables. When we look though at the curve that expresses each one of those, the curves are similar. They're not the same, definitely, but they are similar. And they have the shape of what you see on your screen, the bell-shaped curve. All of them, they are symmetric. They are symmetric around the mean. And the mean of the x variable falls exactly where you see in the middle of the curve. Also, because of this symmetry, the mean, the median, and the mode of the normal distribution are the same. They are not specifically equal to a number. They can be equal to any number depending on the variable, but mean, median, and mode are equal. Also, we have easy ways of calculating the standard deviation and to know exactly where each one of the points, each one of the values of the x variable stands and how far away from the mean they are. And this will determine the standard deviation on our graph that we will discuss in a moment. Now, since this curve represents nothing else than a distribution, a probability distribution, and we have seen probability distributions in the past, the x-axis represents all the values that the variable x can take, and the y-axis, because after all, it's just a graph, there is a y-axis. The y-axis represents the probability that the specific value of x takes at a specific point. So, for example, if in the distribution that you see on your screen, the mean is equal to 5, then the point up here on the curve will give me what is the probability for a specific value x to be equal to 5. So the top, the y, the corresponding y for the mean is going to be the probability that the x is equal to the mean. In exactly the same way, we can calculate the y value for each one of the points of the curve. Since these are going to be probabilities, all these probabilities are going to be numbers less than 1. The total area under the curve is equal to 1, and it is equal basically to the sum of all these different probabilities. Now, let's look a little bit the curve more carefully. Always, for any normal distribution that we work with, we have the middle point to be the mean. And then from the mean, either to the right or to the left, until we reach the tails of the normal distribution of the curve, we expand the x-axis by 3 standard deviations. It's not exactly 3, it's 3.5, around 3.5. One thing that you need to remember is when you look at the normal distribution curve, the curve never touches the tails. It extends forever, supposedly, but it approaches the curve. The curve goes asymptotically to the x-axis. So what does this mean? This simply means that if we go further to the right on the curve, then the probability for the x to be a number over here is going to be very, very close to 0. It's going to be something like 0.000000009 or something like that. Because remember, this is what the curve represents, the probability for each one of those points. Now, the curve has inflection points. The inflection points that you see on the curve, no matter what the distribution is, the inflection points that you see on the curve are happening exactly at 1 standard deviation away from the mean. Okay, so this is always like that. Now, from the left tail to the right tail, the total distance is exactly 6 standard deviations, so 6 sigma. This is where the title for the association also comes, the 6 sigma. Now, let's continue looking a little bit on the curve in order to make sure that we do understand what the curve represents. So by looking at the curve, what we see is that we can have different type of curves. They all look similar, but the one is more flat, the other is more pointy. So the narrower the curve that we have, like in graph B, it simply means that from the mean to the tail, we have a smaller distance. So this means that the 3 standard deviations have a smaller distance from the mean. So simply this means that the standard deviation is smaller for this type of curves. While for a flatter curve, like this one, the standard deviation is bigger. The mean is exactly at the point that this describes, like 3.5, 3.5, while on the curve C, as you can see, that is basically transferred on the left, the mean is 1.5. Again, the inflection point always, no matter what the curve is or where it stands, they show you 1 standard deviation to the left and the right of the mean. So now looking at that and making sure that we understand what we review right here, if we look at the curve A, the mean is 15. When we look at the curve B, the mean is 12. If we look at the curve A also, we see that from 15 to 12, we have exactly 3 units. So this means that the 3 standard deviations are 3 units, so the standard deviation is 1. While if you look at the curve B and you go from 12 to 6.5 almost, this means that we have 6.5 total units, almost 7 total units. So the standard deviation will be 7 divided by 3. So it's going to be 3.3. 2.3, I'm sorry. Let's look at an example. So what do we have here? We have we have a normal distributed population. That is the population of the grade 8 mathematics test for New York State. The mean is at 6.75. So now if we have the 675, that is the mean, or if we have just the actual graph here, we can immediately find what the mean is, and by looking at the inflection point, we can find what is the standard deviation. The standard deviation, it happens at 710, so this means that it's 35 units points away from the mean. The standard deviation is 35. Now, standard deviation, being so important, has had in the past been the research subject for many statisticians. And I'm talking about decades ago, when we didn't have computers yet. So they realized that in order to calculate and to run hypothesis tests and to calculate anything regarding the normal distribution, they need to actually calculate the probabilities. Now, looking at the curve, to calculate the probability for any specific x value, what I'm looking at, let's say x value equal to 1 for this, that is the standard normal distribution, the standard bell curve. This simply means if I want to find the probability for x being less or equal to 1, this simply means that I want to find the area of this curve up to the vertical line that crosses the x-axis at 1. Okay, so imagine that you had a vertical line right here. To calculate this area, there are two ways for us. In the past, there was only one way. To make the calculation, to do the calculation, we have to find the integral, the definite integral for the specific density function of the normal distribution. And you discussed about the density function in week 9 of Predict 400. So you have to actually calculate the definite interval. So this means in order to calculate any probability for any point right here, what you need to do is to calculate the integral. But because of the symmetry of the normal distribution, every time that you calculate this probability for any one of these distributions at specific points that they are proportional to the curve, you will find exactly the same answer. The probabilities will be the same. So they thought decades ago, without computers, why should I calculate the integral every time? Let's sit down, take a specific normal distribution, calculate all the probabilities for the x's from negative 3.49 to positive 3.49 that cover the entire, basically, area, the entire distribution, put it on a table, and from now on, instead of calculating using integrals, I just use my table like an abacus in order to actually find the number immediately. So this is what they did, and they came and they created this table that we call the z-score table. The z-score table, in the middle of the table, what it has are the probabilities, that they are nothing else than the area of the curve for the part of the curve that is to the left of a specific x. So if I'm looking for this x right here, this blue area right here is going to correspond to the probability for the x value to be less or equal than this specific x. So what they did is that all these probabilities, they just put them in these beautiful tables. Okay, now on the first column and on the first row, they put down the z-score, as we call them, that these are numbers that they can be reviewed. Like, for example, look at the 0.8554 right here. This is the probability for the x to be at the left of what number? Of 1.06. So what you do is you append 1.0 with 0.06, add them up. But when you have a negative number, you don't add them. You basically append those two numbers. So what I was looking, this one, 0.8554 is going to be the probability for the x to be less or equal to 1.06. Okay. For what distribution, though? Well, that's the whole point. They had to choose one distribution, and they did. They chose the distribution where the mean is equal to 0 and the standard deviation is equal to 1. So if I'm calculating the probability for 1.06 as I did above, basically what I calculate is for this specific curve over here, the probability that the x or the z is at the left, meaning less than 1.06. And it's 0.8554, okay? So the probability is basically 85.54%. Now, probability and area is exactly the same thing in this case because probability of the total distribution is 1. The area of the entire curve under the curve is 1. And we are talking about the same thing. So the probability and the area to the left of 1.06 is going to be this blue part right here. And is what? Is 0.8554 when the entire area is 1. Okay, beautiful. So I do have my numbers on this table for the standard normal distribution. And it's lovable. But the thing is, how much does this help me? My distributions can have any mean and they can have any standard deviation, right? Right. In this case, is the 1.06 a number that I can find in any one of these curves? Well, yes, it is a number that you can find everywhere, but this doesn't mean that they will have exactly the same probability because the numbers will be different depending on the distribution. So we call z-scores the numbers that we see on the standard normal distribution. And because of the symmetry of the normal distributions, we are able to translate from one distribution to another distribution using a very easy formula. The formula that you see at the bottom, z equals to the value, the x value, minus the mean divided by the standard deviation. So if you do x minus mu divided by sigma, then you can translate any x for any different distribution with mean mu and standard deviation sigma into a z-score. You can translate the x, find the z-score, go to the table, calculate the probability, and the probability that you will get will be the same for the actual distribution that you start with for the value of x. So this is what we do. We start with a normal distribution with mu and sigma. We take the formula to translate any x value into the standard normal distribution, and we get the information here from the z-score table. So let's say the cumulative area is close to 0 for these scores close to z equals to negative 3.49. This is why the z-score table starts from negative 3.49 z-score to positive 3.49. For anything else, you can assume that the probability is 0. The cumulative area for z equals to 0 is exactly 0.5 or half for the mean. So the z equals 0, it means the probability for the x to be less or equal than 0. But 0 is the mean. And because the distribution is symmetric, this means that the probability will be exactly 1/2. Let's see now how we actually calculate the cumulative area that corresponds to a specific z-score. I'm sorry, I'm going to do only one example. Let's say here, suppose that you have your z-score 1.15. This is your z-score. Let's go here. Okay, 1.15 is going to be somewhere here, right? Right. Now, do you remember the empirical rule? What the empirical rule says? The empirical rule says that if we are one standard deviation away from the mean, then the 64% of the entire population falls in, I'm sorry, in this area. Okay, so from -1 to 1, I have I'm sorry, from negative 3.49 to 0, I have 0.5, so 50% of my area. Now, from negative 1 to 1, I have 64% of my area. Since it's symmetric, from 0 to 1, it will be half of it. That is 34%. If I add 50% plus 34%, this gives me 84%. Since my number is at point 1.15, that is somewhere here, then this means that I expect that the probability will be around 85%, 85, 86, somewhere there. So let's verify that with the z-score. 1.15. 1.15, what do? You split it into two different numbers. 1.1, the first two numbers right here, and you find the 1.1 on your z-score table right here, and 0.05, and you find this number right here. Then you go to the row and column that corresponds to that number. The number is 0.8749. And what is this? This is the area to the left of 1.15. So it's 0.8749 or 87.49% probability to have an X or a Z that is to the left of 1.15. This is what this tells me. Remember, sometimes they ask you for cumulative area, sometimes they ask you for probability. Basically, they ask you for exactly the same thing. Does it make sense? Do you have any questions up to here? Okay, let's do another one. Find the cumulative area that corresponds to a z-score of negative 0.24. You do exactly the same. Split the number 0.2, negative 0.2, and 0.04. That's why I'm saying you append the numbers. So you find the 0.2 here, negative 0.2 here. You find the 0.04 here, and you find the corresponding number right here. That is 4052. 0.4052. What is this? This is the cumulative area or the probability. So the probability is less than 50%. My number is negative 0.24. Let's go here. Negative 0.24, it's somewhere here, right? From 0 to the left, I have 50% of my area, 0.5. Since my number is to the left, the number that I expect for the probability or the cumulative area is going to be a number less than 0.5, of course. Now, since this part of my area under the curve is the fattest part, this means that cutting down this column right here from negative 0.24 to 0 from the area, then this means that I would cut a quite significant amount of possible X values. That's why I drop to actually 0.4052. So it is something that I would expect. Okay, in the same way, this is how I calculate, this is how I use the z-score. Every time that I have the z-score, this is how I calculate the cumulative area to the left. This is the blue area for 1.3, 0.23, I'm sorry. And this also corresponds, since this curve represents nothing else than the probability distribution, then definitely this blue area refers to the probability for my z to be less than 1.23. Now, what happens if I want to find the cumulative area to the right of a specific z-score? Or if I want to find the probability for a specific z is greater than a specific z-score? Well, these two cases can be solved in the same way. you are looking again at the z-score table for 1.23. This is what you do. And if you look at the z-score table and you go to 1.23 right here, the number will be 1.2 right here and 3 right here. So it's going to be, as you can see, 0.8907. But what is this? This is the cumulative area to the left of the z-score. I want this part right here. But what is this part? This part is 1, that is the total area, minus what I just found, the blue part. So basically, in order to make these calculations, what I need to do is to subtract what I find in the z-score table from 1 and come up with the final answer. Okay, that is 0.1093, so 10.93% probability for my value z to be greater than 1.23. And what is happening if I want to find the area between two z-scores? Well, again, I use the z-score table and I calculate to the left of the leftmost and to the left of the rightmost. So the z-score for the leftmost is 1.23. I calculate, the rightmost is 1.23. I calculate this, that is 0.8907. I calculate the same for negative 0.75. So this number right here will represent this blue area right here. This pink area right here. And then I subtract from the blue area, from the 1.23 to the left, the pink area that is right here. And the result is 0.6641. In the same way, I can calculate many different z-score and I can find the areas for many different z-scores. I can find, the area for specific z-scores. I'm not going to do more examples on that. You know how to do it. Now the question is, how do we find specific probability given z-scores, and how to find z-scores given specific probabilities. So let's look at this following example. Let's assume that this is the distribution for the SAT scores. What do I see right here? It's not, but let's say that it is. Let's assume that the mean is equal to 500, as you can see, and let's assume that the standard deviation is 100. Okay, I want to find the probability that the x is less than 600. So assume that I have, that I myself have taken this SAT score and I want to find the percentile to which I belong. In order to find the percentile to which I belong, basically I want to find the probability that any other student got a lower score than me. Okay, this is how I find the actual percentile. Okay, so how do I do that? The distribution that I have is not the standard distribution, so I don't have z-scores here. I have x values. In order to calculate the probability, I really need to calculate the area, the blue area right here. What should I do? The first thing that I need to do is to translate my x, that is the 600, into a z-score. Then I will go to the z-score table and find the corresponding probability that it happens to be exactly the same with this probability right here because of the symmetry. So, this is my normal distribution. These are my numbers. I use the formula z-score equals to x minus mu divided by sigma. The z-score is 1. So in the standard normal distribution, I have 1 right here and 0 here. And I'm looking for the probability for the z to be less than 1. I go to the standard table, the z-score table, that is up here, and I'm looking at 1.00. That is 0.8413. I go back to slide, I don't remember what slide I had, I think 30. Okay, yes. And I know now that the probability of z-score less than 1 will be equal to the probability of x less than 600. So the probability for that will be exactly, do I have it anywhere? I don't have it anywhere, it doesn't matter. The probability for that will be 84%, 84 point something, as we just calculated. Another example. A survey indicates that people use their cellular phones an average of 1.5 years. So I guess I'm behind because I have my phone for 3 years before buying a new one. The standard deviation is 0.25 years. A cellular phone user, so if the standard deviation is 0.25 years, then this, and I have my phone for almost 3 years now, then this means that I am, if you look at your numbers, 1, 2, 3, 4, 5, 6, 7, 8, 8 standard deviations away from the mean. Okay, the cellular companies cannot depend on me to make money. A cellular phone user is selected at random. Find the probability that the user will use their current phone for less than 1 year before buying a new one. The normal distribution that we have about the years that we use the phones has a mean of 1.5 and a standard deviation of 0.25. Now, we want to find the probability for less than 1 year on the original distribution. We plug in the numbers. 1 minus 1/2 divided by 0.25 is equal to -2. -2 is going to be the z-score for this. And if you go to the z-score table and you calculate the probability for the z to be less than -2, you will find that the answer is 0.0228 or 2%. Another example. A survey indicates that for each trip to the supermarket, a shopper spends an average of 45 minutes with a standard deviation of 12 minutes in the store. The length of time spent in the store is normally distributed and is represented by the variable x. A shopper enters the store and finds the probability that the shopper will be in the store for between 24 and 54 minutes. So now here we want to find the probability to be in a specific interval. So we want to calculate probabilities for 2 different z-scores, okay, after we translate our distribution to the standard distribution. So we want the probability for this person to stay in the store between 24 and 54 minutes. Okay. In order to do that, if the mean amount of minutes that one stays in the store is 45 and the standard deviation is 12, then I can translate using the formulas to -1.75 for the 24 and to 0.75 for the 54. So you look right here and you see exactly the numbers, the z-scores that correspond to this distribution. So now I want to calculate the probability for the z-score to be between this and that. Okay, again I need to go to the z-score table, find the probability for the z to be less than 0.75, find the probability for the z to be less than -1.75, and then subtract those 2 probabilities right here to get 0.7333. So there is a chance of 73% that a person stays in the store between 24 and 54 minutes. So in this way, actually, we calculate the probabilities. Here is another example, or another version of the same example for a person that stays in the store 39 minutes. So in this case, I'm looking to the right side of the curve, right? And I translate again, I find the probability, but now I want to find the probability for the z-score greater than that. So I will look at my z-score, I find the probability, and I will subtract it from 1. 0.69, 15 is the answer. Okay, so we got the idea of how we actually calculate probabilities given either specific means and standard deviations for different distributions or specific z-scores. Now, let's try to look at the same problem the opposite way. What do we have to do? We need to find the z-score that corresponds to a cumulative area of 0.3632. So now we have the cumulative area, or we have the probability for something to happen, and we are looking to see what is the z-score, or what is the x value for the specific distribution that we are looking for. Again, we will be working with the z-score table. The probability that we have, the cumulative area that we have, is 0.3632. We go to the z-score table and we try to find the 0.3632. That is right here. This 0.3632 number corresponds to negative 0.35. So that's the z-score that I'm looking for. So you look at your table, if you have the probability, you look at the middle of the table, you find the probability, and you corresponding to the z-score that you can get from the row, from the first column and the first row. So this is how we find it. Now, if I want to find a similar problem, find the z-score that corresponds to 10.75% of the proper distribution to the right, then I will find the number. I will subtract this number from 1, because the z-score table always works with the left side. I will find the corresponding number, that is 0.8925. And then I will look in the z-score table for this number right here in order to find the z-score, the corresponding z-score. And the z-score will be 1.24. Okay, that's enough. This is the idea of how to transform between z-scores and probabilities in general. When I have populations, but you will rarely have populations. The most of the times you are going to work with sampling distributions. Okay. So before we go on and we look into sampling distributions and we look what exactly is the difference by looking in a sample instead of looking in the entire population, I want to mention right here that the formula that I gave you that calculates the z equals to x minus mu divided by sigma, it can also be written as x equals to mu plus z-score times sigma, and this can give you the corresponding x. So if I have a problem like this, a veterinarian records the weights of cats treated at the clinic. The weights are normally distributed with a mean of 9 pounds and a standard deviation of 2 pounds. So I have my distribution here, and this follows the normal distribution. Then we want to find the weights that correspond to z-scores of 1.96. Let's forget about the rest. So what I need to do, if I have my mean and I have my standard deviation, I will use this formula now, the same formula in another format basically. I will solve it for x and I will get the actual weight that corresponds in this probability to a specific z-score. Now you will tell me, why would I ever care to do that? Well, you will, because usually what you are going to get when we will start our hypothesis testing is that you will start with a confidence level that you want in order to run your hypothesis test. Sometimes you want to have a high confidence level, so something like 99%. Sometimes you would like to have confidence level that is lower, let's say 90%. Now, always we want to have high confidence level when we work with hypothesis tests, but sometimes it gets very expensive. That's why we can accept lower confidence levels in some cases. Now, when you know what is the confidence level that you want, like 95% or 99%, and then in order to run your test and you calculate basically what is the interval that you believe that your parameter, either mean, standard deviation, variance, or even proportion is for your population, you have some lower and upper bounds for your confidence level. And these numbers are coming from the standard normal distribution. So it is possible, and it will be all the time from now on, that you will start with your z-score, like the 1.96, and you would like to know what this z-score corresponds on your distribution in order to calculate the confidence levels. But we will come back to confidence levels next week, actually. So, I'm not going to run another example here. You get the idea of how to calculate everything in this problem. So let's start talking a little bit about sampling distributions and the central limit theorem that are extremely important for us. Sampling distributions, and to understand how these sampling distributions connect to the populations. Again, I want to remind you that from now on and for your entire career, you will be working with sampling distributions and you will rarely look into actual populations. That's the whole point of using statistics. We would love to have access to the entire populations. And when we do have access to entire populations, we would love to be able to handle the amount of data that we can collect and we can have. But we rarely care to look at the entire picture. We are focusing on samplings, random samples that we have selected correctly, that they help us model and actually understand and forecast measures for the entire population. Okay, sampling distribution. The probability distribution of a sample statistic. So, for example, I have mean. I have the mean. This is my statistic. The probability distribution for the sample statistic, so I have a set of samples from an entire population, and I'm focusing on the means. I have a variable. Let's assume the same variable, like the amount of time that the professor takes to grade. And then I have a sample. I have all the professors that they teach statistics, all the professors that they teach English, all the professors that they teach biology. And then I take the sample statistics for each one of those samples. So the mean, the average time that they spend grading. The probability distribution of these numbers is what we call the sampling distribution. So basically, we start with the population, we create samples of some size, and then we look at the statistics of those samples. Sampling distribution of sample means, or sampling distribution of sample standard deviations, is the most common example and situations that you may have. So again, look at it at the big picture. You have the entire population, you take specific samples, but sometimes they may overlap, it doesn't matter. And then you look at your statistic, that it may be the mean, for each one of those samples. Okay, then you create the probability distribution for these samples. The mean of the sample means will be denoted by mu x hat, and this is your mu for the specific sample distribution. While the standard deviation is going to be the standard deviation for the entire population divided by square root of n. So what do we see here? The mean of the sample means is the same with the mean of the population. The standard deviation, though, is not the same. It really depends on the sample size. So the standard deviation becomes basically smaller for the sampling distribution. And it depends on the sampling size. This is going to be especially important for you when you are going to create the sampling distribution. So sometimes you want bigger or smaller samples depending on the needs of your analysis. This is what we call the standard error of the mean. So the population values that we have here is 1, 3, 5, and 7, and they are written on slips of paper and put in a box. 2 slips of paper are randomly selected with replacement. We find the mean, the variance, and the standard deviation of the population. So we look at the entire population here, and we calculate the different measures. We graph the probability histogram for the population. And since we have exactly 4 values, each one of these values has a probability of 0.25% to 0.25 or 25% to happen. That's the probability histogram for the entire population, for the population values. Now, we look at the means for each one of the different samples of size n that we can have. So we take all the different combinations of the numbers 1, 3, 5, 7 that we may have. These are the ones that you see on your board. And we calculate the mean for those samples. So with red, you see the means of those samples. Up to here is simple. Okay, now you look at the sample means and you calculate the frequencies and the corresponding probabilities for those numbers to exist. So for example, to have a mean of 1, the probability is 0.0625. Because the mean of 1 you will have only if you have 2 1s in your sample, right? It's very small. This is the way that you calculate the rest of the probabilities. Okay, so we did all that. We calculated all the numbers. Now we want to graph the probability histogram for this sampling distribution of the sample mean. What did you realize? Looking at the histogram, it's obvious that this histogram is very symmetric and very well bell-shaped. So what happened? We took a population. In the specific example, it was a uniform population where each one of the variables or each one of the values in the population appeared once. Very simple one, a uniform population. We created the means with size 2 and looking now into the probability distribution of the means of those samples, we have a bell-shaped histogram. What does this mean? This is basically what the central theorem tells us. The central theorem tells us one thing, that whenever we have a distribution, it doesn't matter what distribution, although there are some exceptions. But in all the cases, the central theorem tells us that if you take any kind of distribution and you take samples of this distribution and you take metrics, meaning statistic for those samples, and you look at the probability distribution of those, then the corresponding probability distribution that you get is normally distributed. So it approximates the normal distribution. And this is a beauty. And it is a beauty because it simply means that no matter what distribution I have, I am able, instead of looking at the population, to look at parts of it, subsets of it, that they are nothing else than samples, and translate this distribution of the population that I have no idea how to handle it, because it's anything, it can be anything, into a normal distribution. And it's major. And this is the last reason that made the normal distribution so important. Now, in your book, and in every book, the authors tend to say that if you have samples of size n greater than 30, then any sampling distribution of the sample means approximate a normal distribution. And this is what the central theorem says. But the central theorem also refers to exceptions. And it's not true that any sample of size n greater than 30 can take us to the normal distribution. The Black's book says that n must be greater than 30. The Wilcox book says that n must be greater than 40. The common rule says that the n must be greater than 36. The truth is that it's possible that you have a distribution that it is greater than 30 or 40, but it has extreme outliers. And if the distribution has enough extreme outliers, then it will not approximate to a normal distribution. So this is one of the exceptions. There are other exceptions that I would like us to discuss later tonight as well. So what's the rule of thumb? The rule of thumb, I would say, is, first of all, do you have extreme outliers? If you have extreme outliers, be careful. Do you have other conditions that make you believe that it's not going to approximate the normal distribution? Special situations, special type of data set, then be careful. If you don't, then to assume 36 or more data is good. You can do it. But in order to be sure that at least all the other conditions except of the extreme outliers can be covered, you need to have a data set of 200 and above. How important this is? Well, these type of calculations and these types of inferences and simplifications by people that they work in responsible positions as data analysts can take us down to 2008 and Lehman Brothers being actually bankrupt. So be very careful how you use your numbers and how easily you decide to simplify quite complicated theorems as such. Okay. I have more examples here for the central theorem, specific examples, that it would be a good idea to review them, because the idea of taking the sampling distribution of specific statistics for the population is not that clear the first time that you go through. So if you feel that it's not 100% clear what you're doing right here, then that's why I have this extra example here for you. Make sure that you review it. It is important. Before I go on to the next example, I want to tell you that when you calculate the z-score because of the central theorem, and when you calculate the z-score in order to transform a sample mean, and you're looking in a sample that is normally distributed, then you don't divide your formula by the sigma, by the standard deviation of the population, but you divide your formula by the standard error, that is the sigma divided by the square root of the size of the sample. So let's see one example like that. What do we have? We have randomly select 50 drivers between the age of 15 and 19. What is the probability that the mean time they spend driving each day is 24.7 and 25.5. The standard deviation is 1.5. So we are looking right now in a sample of 50. The standard deviation for the population is 1.5. We assume that we can approximate the sample with normal distribution because of the central limit theorem and because we assume that we don't have extreme outliers. So we are looking at our answers, calculate our mean. The mean is going to be the same with the mean of the population. The standard deviation, the standard error is going to be the sigma divided by the square root of n. We plug in now the values in the corrected formula, that is 4 samples, and we follow exactly the same process as we did before in order to calculate the probability in order to be on the specific interval. We look at the z-score table for the specific z-scores negative 1.41 and 2.36, and we calculate the probability to be 91%. Okay, one more example for you here. And at this point, we discussed everything that has to do with the basics of normal approximation. I'm sorry, normal distribution. What I want us to focus now is the second reason why normal distribution is important. And it is important because it can be used to approximate not only the binomial distribution, but also the Poisson distribution and also the hypergeometric distribution that we can discuss hopefully in a while. But let's focus on the binomial distribution in detail right here. What do we have? What are the conditions? In order to have a normal approximation of a binomial distribution, we have to know that the n times p is greater or equal to 5 and n times q is greater or equal to 5. What does this mean? Remember, n is the number of trials, p is the probability of successes for the binomial distribution. So if n times p is greater than 5 and n times q is greater than 5, then you can approximate with the normal distribution. Okay, these conditions are important, are very important. You cannot approximate with normal distribution, a binomial distribution, if the n times p or the n times q is less than 5. And this can be done very easily. For example, if I have the probability of success of I don't know, something that is very successful and it's 0.99, very high probability. And I run the same thing 100 times. Then, although 100 times 99 is going, 0.99 is going to give me 99. That is greater than 5. The Q is going to be 0.01. And if I run it for 100 times, then the n times Q is going to be 1, and the 1 is less than 5. So in this case, I cannot approximate with the normal distribution. So what does this mean? When I can and when I can't, as a rule of thumb? Well, if the probability of success is close to the probability of failure, so it's 0.6, 0.4, 0.5, 0.5, 0.45, 0.55, numbers like that, and I do have a high number of trials, then your numbers are going to be greater than 5. If your probability, I'll give you an example. If your probability is 0.5 for both, and you have 10 trials, then this works, because NP and NQ is equal to 5. So it doesn't depend only on the probability, but it depends on the number of trials. So they are interconnected. The biggest probability, the biggest of the difference that you have between the P and Q, the more number of trials yet that you need in order to approximate it with a normal distribution. Let's look at this graphically. So what do we see on our graph here? On the top, we have 4 trials, and the probability is 0.25 in each one of the cases. So with 4 trials, you see the histogram. It doesn't look like normal distribution. It doesn't look like a bell-shaped histogram. Then, when the trials become 10, the NP is 2.5, the NQ is 7.5. The NP is 2.5, it's lower than 5, and you see that still we don't have a bell-curved histogram. When the N becomes 25, then both of them are higher than 5. And now, in this graph, on the bottom left, you can see that the graph looks like a bell histogram. As the N increases to 50, the NP and the NQ increase as well, and the graph becomes more and more looking like a bell curve. So this simply means that the binomial distribution looks more and more like a normal distribution, so we can approximate it using normal distribution tools. So let's look at an example. Just a moment. Before I look at the example, let's look at an example first. Decide whether you can use the normal distribution to approximate the X. We have 62% of adults in US that have HDTV in their homes. You randomly select 45 adults in US and ask them if they have an HDTV. Well, we have trials 45 adults. The probability for success is 0.62, so the probability of failure is 0.38. So NP is 27, NQ is 17. So definitely you can use the normal distribution because both of them are greater than 5. If you do the same here, in this case where you have N trials 30, but the probability of success is much smaller, 0.12, you can see that you cannot use it. You need a bigger data set, you need more trials here. Now, looking at the graph of the binomial distribution with the histogram and the bars, and looking at the curve of the normal distribution, what we can observe is that although there is an approximation, we still, in the case of the binomial distribution, we have a discrete variable. So we do not have a smooth curve. We have the different columns, the different rectangles of the histogram. If you look at the blue rectangle right here, you will see 2 things. On the top of the rectangle, I have an area, a small triangle, a curved triangle, that is outside my rectangle. And on the right side right here of the blue rectangle, you can also see that I have a small triangle that is inside the binomial distribution, but is not part of the normal distribution. Now, this one and these ones, they smooth out themselves, but not completely. So what do I need to do? What I need to do is to consider a correction for the continuity whenever I look into intervals for the binomial distribution. So if I work with specific numbers, like for example, I want to run trials and see that I have a number of successes, anywhere from 270 to 310 successes of a specific trial. Then in order to, the correction for the continuity, it would mean that for this interval, I need to include that blue parts of my normal distribution that I showed you before. And in order to do that, in order to smooth out that and to correct it, what I need to do is to consider a small piece of interval to the left and another to the right in order to make the interval bigger to include the entire normal distribution interval. Okay, so whenever you calculate, whenever you approximate a binomial distribution by the normal distribution, and you look at your interval, for the bottom left border, you have to subtract 0.5. For the upper right border of your interval, you have to add 0.5. In some cases, you will have the entire interval. In the case that you want to have from these many successes to these many successes. So you have to expand your interval by 0.5 to left and right. In the case that you want at least these many successes, then this means that your interval starts from somewhere and goes to the maximum number of trials. So your left border is the one that needs to be expanded to 0.5. You have to subtract 0.5 from 158 in this case. So you want the x to start from 157.5. In the case that you want to have anything greater than 63, less than 63, again, you subtract 0.5. If you wanted to have at most, let's say, 100 successes, then your interval should go to 100.5. So always remember when you do your calculations with the normal distribution to actually add from the left and subtract from the left and add to the right a 0.5 for the correction of the continuity. Okay, this is an example that I have here for you, but because it's already 8:30, this example is quite explanatory and simple and shows you the actual correction of the continuity. Review the example yourself. Let's do that. Review this example and look at the calculations that I have here. And if you have questions, let me know. Again, you can see here the correction for the continuity. Since I want 96, I start from 95.5 and I go to 96.5. Do that, and we are going to discuss now the second set of notes that I have prepared for you. Okay. Okay, what I have right here for you and I want you to see is, as I said before and as we discussed, the three distributions, binomial, hypergeometric, and Poisson. What I want to show you here with this slide is that there are some cases that the three distributions can become very similar. And I have specific examples here, and I don't know if you can see them. It's not very clear. The n is greater than 100, and the p is 0.1. So the p, when the p is small, is very small, and the n is big, then in this case, this is the situation that we have. The n is very big and the p is very small. Then all the three different distributions, they are very similar. What does it mean that they are very similar, and why do we care? Well, sometimes, for example, if you have a hypergeometric distribution and you're looking at a specific data analysis in the specific data set where you have a hypergeometric distribution, but you have very small p and too many trials, you have too many data points. Then, instead of looking at the specific of the hypergeometric, you can actually look at the binomial distribution. So that is much easier to calculate, and then you can approximate it with a normal distribution as well. So in this case, there are tools that you can use that they connect, they interrelate the three distributions. And this is important, and keep this in your notes so you know when those distributions are similar and you can jump from the one to the other. Also right here, I have the formulas in R that you can use to actually calculate those specific exact, these are for exact calculations for the binomial, for the Poisson, and for the hypergeometric. Now, again, as I said, we didn't spend enough time last week in hypergeometric. So what I have here is the definition of the hypergeometric distribution, only to make sure that you know what it is and what it refers. It is basically the same with the binomial distribution, except that we don't have replacement. So imagine that you have an urn. This is the most easy and the most common example that we give, the books give. You have an urn and you have black balls in the urn, marbles, and white marbles. Now, if you select one and you have, let's say, 60% white marbles and 40% black marbles, then if you select a marble, if you select 100 marbles with replacement from that urn, so you pick a marble and then you put it back, you pick a marble and then you put it back. Basically what you have is Bernoulli trials, binomial distribution, and you can record your data from these experiments and you can run them and you will see that what you have is a binomial distribution. If you do it 100 times, you will see that your histogram will approximate the normal distribution as well. Now, in the case that you have exactly the same situation, but every time that you pick a marble, you don't replace it. So you take it and you put it out. Then immediately what happens is that the trials are not independent anymore. So you don't have binomial distribution. In this case, what you have is a hypergeometric distribution. So this is the example. This is what hypergeometric distribution is, and the formula that you see on your board is how we calculate it.